There's something happening right now, in this very moment, that most of humanity has absolutely no idea about. 93 million miles above our heads, the sun, that seemingly quiet, eternal furnace we see every single day, just unleashed one of the most violent outbursts of energy it's produced in living memory. And what makes this event absolutely extraordinary is that it exceeded every prediction, every model, every expectation that our best scientists had prepared for. This is the story of the solar radiation storm that broke all the records. This is a story about cosmic violence, about the delicate systems protecting us, and about what happens when the universe decides to remind us just how small we really are. Let me take you back to the moment it started. On the surface of the sun, in a region called an active region, magnetic fields had been building pressure for days. Imagine these magnetic fields like coiled springs, getting tighter and tighter, storing more and more energy with each passing hour. The sun's atmosphere, the corona, was twisted and contorted into impossible shapes. Plasma, that fourth state of matter, hotter than the surface of the sun itself, was being held in place by these magnetic field lines, like invisible ropes restraining an unimaginable force. But here's the thing about pressure. It always seeks release. And when the sun's magnetic field finally reached its breaking point, what happened next was utterly catastrophic. A solar flare erupted. Not just any flare, but an X-class flare, one of the most powerful categories possible. In just 10 minutes, this flare released more energy than all of human civilization uses in an entire year. Think about that for a second. All the electricity flowing through our power grids right now, all the gas burning in our vehicles, all the coal consumed in power plants around the world, all the oil refined into fuel, all the nuclear reactors splitting atoms, all of that combined, for a full year, equals what the sun released in 10 minutes. That's the sheer magnitude we're talking about. The temperature in the flare region skyrocketed to millions of degrees. Atoms were torn apart. Electrons were stripped from their nuclei. The bonds holding matter together were violated. X-rays and gamma rays flooded outward at the speed of light, carrying energy that would make nuclear weapons look like firecrackers by comparison. But that flare was just the opening act. The real event was what came next. A coronal mass ejection, a CME, blasted outward from the sun billions upon billions of tons of plasma, superheated, magnetically charged particles, accelerated to speeds exceeding 2,000 miles per second. That's not a typo. 2,000 miles per second. If you traveled at that speed, you could reach the moon in 6 seconds. You could circle the entire Earth in about 9 seconds. You could travel from New York to Los Angeles in less than a second. At that velocity, the plasma ejected from the sun tore through the solar wind like a knife through butter, carving out a shock wave as it went, creating a bubble of intense disturbance that expanded outward at nearly the speed of a nuclear explosion. The particles in this CME weren't all traveling at the same speed. The cloud had structure. The fastest particles at the front of the wave were moving at relativistic speeds. That is, speeds where Einstein's special relativity becomes important. The effects of time dilation, length contraction, and the increase of relativistic mass all became significant. Some particles were traveling at 90% the speed of light. Some were faster. These weren't just particles anymore. They were projectiles with cosmic-scale energy, capable of penetrating matter that would normally stop radiation dead in its tracks. Scientists measured proton energies reaching into the hundreds of millions of electron volts. To put that in perspective, the most powerful particle accelerator humans have ever built, the Large Hadron Collider at CERN in Switzerland, accelerates particles to energies in the tera-electronvolt range. But the sun was doing this acceleration naturally, with no technology, no massive infrastructure, just the raw power of its magnetic field and the kinetic energy of the explosion. The sun was, in essence, running a particle accelerator billions of times more powerful than anything humanity has built, and it was doing it without even trying. Now, here's where the story gets absolutely critical for understanding why this event was so unusual and so dangerous. The sun's magnetic field wraps around the entire solar system. The solar wind, a constant stream of particles emanating from the sun, carries this magnetic field outward, creating what we call the interplanetary magnetic field. Normally, this field is relatively weak and benign. It protects us from galactic cosmic rays, those high-energy particles that come from somewhere else in the universe. but it doesn't significantly disrupt our technology or endanger our lives. However, when a CME occurs, everything changes. It carries with it an intense magnetic field, far more powerful than the background field. The field lines in the ejected plasma are so tangled and intense that they form what's called a magnetic cloud. Inside this cloud, the magnetic field strength can be 20 times stronger than the normal interplanetary field. This intense, turbulent magnetic field drives the acceleration of particles to those extraordinary speeds. The particles are accelerated by the shock wave riding in front of the CME. They're accelerated by the magnetic field lines compressed in the ejecta. They're accelerated by secondary shocks and waves that form as the whole structure propagates through space. By the time these particles reach Earth, they've been accelerated through an energy gain that would require the most powerful human-built accelerators on the planet. The Earth received the initial warning first: electromagnetic radiation. The light from the flare reached us in 8 minutes, traveling at 186,000 miles per second. Scientists detected it through X-rays and ultraviolet radiation. The wavelengths of this radiation are incredibly short. X-rays have wavelengths on the scale of atoms. Ultraviolet light, the kind that burns your skin when you spend too long in the sun, is intense beyond anything we experience at the surface. These high-energy photons flooded through space and struck Earth's outer atmosphere. The solar observatories positioned around Earth and in space, SOHO, GOES, the Parker Solar Probe, and others all simultaneously recorded the event. Within minutes, alerts went out to space agencies, power companies, and communications networks worldwide. Everyone knew something big was coming. The phones started ringing. Emergency response teams mobilized. Forecasters at NOAA's Space Weather Prediction Center in Boulder, Colorado, immediately issued the highest alert level. But they didn't know just how big this was going to be. The models and predictions, based on historical data and theoretical understanding, suggested a severe event. Everyone braced for impact, but the actual impact would exceed all expectations. The shock wave associated with the CME, traveling at several thousand kilometers per second, reached Earth's magnetosphere in about 3 hours. Scientists and space weather forecasters watched the data in real time, their eyes glued to their monitors, as the instruments showed readings climbing higher and higher. It was like watching a line on a graph that keeps going up, higher than expected, higher than predicted, higher than anything in the recent historical record. Measurements of particle flux, the number of energetic particles arriving per unit area per unit time, started increasing exponentially. The radiation environment in near-Earth space was ramping up, and the graphs showing the increases looked almost like hockey sticks, angling sharply upward with a steepness that was genuinely alarming. Then it happened. The numbers kept climbing. They went higher than anyone expected, higher than the models said was possible. The instruments showed particle fluxes reaching levels that the models said should only occur, statistically, maybe once every 100 years. Maybe once every 1,000 years. Some measurements suggested this might be a once-in-several-thousand-years event. The scientists must have looked at their screens in genuine disbelief. They rechecked the data. They verified the instruments were working properly. They compared readings from multiple independent satellite instruments to make sure they weren't looking at instrument error. The readings were real. This event was actually happening, and it was worse than expected. Here's what you need to understand about radiation storms in deep space. The radiation environment in near-Earth space is measured in proton flux units, essentially counting how many high-energy protons are hitting a particular area. During a quiet day, during peaceful solar conditions, the flux might be on the order of just a few protons per square centimeter per second. It's such a low baseline that astronauts don't really have to worry about it. The radiation exposure is minimal, natural, something life on Earth has dealt with for billions of years. But during a radiation storm, that number climbs dramatically. During a moderate storm, it might reach hundreds or thousands of protons per square centimeter per second. During a severe storm, it might reach tens of thousands. During this event, measurements exceeded 100,000 in some places. The radiation environment had become not just thousands of times more intense than normal, it had become tens of thousands of times more intense. The entire near-Earth space environment had transformed into a radiation hellscape. If you were an astronaut aboard the International Space Station when this happened, you would have experienced something truly surreal and deeply unsettling. In the span of just a few hours, you would have received as much radiation as you normally would in an entire year of spaceflight. Your radiation detectors would have been alarming constantly, beeping insistently with warnings. NASA would have instructed you to shelter in the most protected areas of the station, away from the external walls. The most heavily shielded areas are near the center of the station, surrounded by as much material as possible to absorb and scatter the incoming radiation. The water tanks, the equipment, the structural elements, all of it becomes shielding. Even there, surrounded by as much protection as the station could provide, you'd still be receiving doses that were concerning. And here's something that astronauts have reported during previous extreme solar events, something that's both fascinating and deeply troubling. They could actually see the radiation hitting them. Not metaphorically, literally see it. When a high-energy particle passes through the retina of your eye, traveling at nearly the speed of light, it creates a distinctive flash of light called Cherenkov radiation. It's the optical equivalent of a sonic boom. The particle is moving faster through the medium of the eye than light normally travels through that medium, and the eye produces a photon as a kind of shock response. Cosmonauts aboard Mir have reported seeing these flashes, these brief brilliant streaks in their field of vision. Astronauts on the Moon during the Apollo missions reported them as well. A single particle traveling at near light speed, hitting the back of your eye hard enough to produce a photon of visible light. It's a visceral, direct experience of radiation damage. You're aware, in real time, that each flash represents particles damaging your cells, breaking DNA strands, killing cells outright, potentially causing genetic damage that could manifest as cancer years or decades later. You're literally watching your own radiation exposure happening, one flash at a time. During the worst radiation storms, astronauts report seeing so many of these flashes that their vision becomes disturbed. It's like constant lightning in the darkness. They describe it as disconcerting, even frightening. Imagine floating in space, surrounded by the most advanced protective equipment humanity could design, and still feeling the constant bombardment of subatomic particles, seeing them hit your eyes, knowing that even with all your protection, you're being damaged at the cellular level. The danger wasn't just to astronauts, though. Satellites orbiting Earth suddenly found themselves in an extraordinarily hostile environment. The delicate microelectronics that make modern satellites function were exposed to a particle bombardment of unprecedented intensity. Every transistor, every capacitor, every logic gate in every computer on every satellite was being bombarded by high-energy particles. For many satellites, this was an engineer's absolute nightmare scenario, the kind of worst-case event that keeps them awake at night. Each high-energy proton that hit a sensitive electronic component could cause what's called a single event upset, or SEU. Here's how it works. A particle comes screaming through space at near light speed. It hits a transistor, a component so small that it's measured in nanometers. The transistor is basically a gate that either lets current flow or blocks it. An electrical signal passing through a transistor represents either a 0 or a 1 in the language of computers. The transistor is a container for information. When a high-energy proton hits the transistor, it creates a cascade of secondary particles. Electrons are knocked loose. Charge builds up. The state of the transistor flips. A 0 becomes a 1, or a 1 becomes a 0. That single-bit flip might be meaningless. It might occur in some chunk of unused memory. Or it might be catastrophic. It might occur in the bit that tells the satellite's orientation which way is up. It might occur in the bit that controls the transmission power. It might occur in the bit that tells a critical safety system to activate. A single bit flip in the wrong place can cause a satellite to malfunction. GPS satellites, which billions of people around the world depend on every single day for navigation, started experiencing degradation. The constellation of GPS satellites orbits Earth, constantly broadcasting timing signals. A receiver on the ground, your smartphone, your car's navigation system, a surveyor's equipment, picks up signals from multiple satellites. By measuring the time it takes for signals to arrive, the receiver calculates its position. The system is staggeringly precise. Modern GPS can know your location to within a few meters. But during the radiation storm, the electronics in the GPS satellites started to malfunction. The atomic clocks that keep precise time began drifting slightly. The transmitters that broadcast the timing signals became less stable. The data being transmitted became corrupted. The accuracy that people take for granted, that ability to know your location to within a few meters, suddenly became less reliable. In some places, GPS accuracy degraded to tens of meters. For civilians, it wasn't a total loss. The system still worked, but it was noticeable. For military applications, for precision agriculture, for financial transactions that rely on GPS timing signals to synchronize computers across the world, for airline navigation, it was significantly more serious. Communications satellites experienced similar issues. A communications satellite is essentially a giant transponder in the sky. It receives a signal from one ground station and retransmits it to another. The signal passes through amplifiers and processing electronics. During the radiation storm, errors in this processing increased. The modulation of the signal, the way information is encoded onto the radio wave, became less stable. Voice signals became noisier, as if someone was listening to a radio broadcast during a thunderstorm. Data transmission became less reliable. Packets of digital information would arrive corrupted. Error correction codes could fix some of the corruption, but during the peak of the storm, the error rate exceeded the correction capability. In some cases, satellite operators proactively reduced their data rates. Instead of transmitting high-definition video, they transmitted standard definition. Instead of transmitting multiple simultaneous calls, they transmitted one. They reduced the quality of service to reduce the impact of radiation-induced errors. It's like a doctor saying to a patient, "We're going to reduce the medication dosage because the side effects are too severe." The satellite operators were essentially asking for less demand on their systems so that the systems could continue to function. Weather satellites, those massive instruments that observe clouds and storms and produce the data that goes into weather forecasts, started showing degradation. The instruments that measure temperature in the atmosphere became less accurate. The instruments that observe wind patterns became less stable. The data streaming from these satellites, data that meteorologists around the world depend on to make weather forecasts, became less reliable. Weather forecasters had to work with degraded data. The uncertainty in their forecasts increased. In some regions, it became noticeably harder to make accurate short-term weather predictions. The economic implications started cascading almost immediately. The loss of GPS accuracy affected agriculture. Farmers using GPS-guided tractors, systems that can plant seeds with meter-level precision, had to switch to less precise guidance. Yields in precision agriculture depend on knowing exactly where to plant and where to apply fertilizer. The degraded GPS accuracy meant less efficient farming. Over the course of a growing season, this adds up to real losses. Airlines flying polar routes, the efficient paths that go over the North Pole on long-distance international flights between North America and Asia, had to make decisions about whether to continue operations or reroute flights. These routes naturally expose crews and passengers to more cosmic radiation because they fly over a region where the magnetosphere is thinner, more porous. The protective bubble of Earth's magnetic field is weaker near the poles. Add in a severe solar radiation storm, and the radiation doses climb significantly. Most airlines continued operations but monitored doses carefully. Flight crews wore radiation dosimeters to track exposure. Dispatchers calculated the radiation dose for each route and made decisions about whether to fly or divert. Some flights were rerouted around the poles, adding hours to the flight time but reducing radiation exposure. The crews received additional radiation exposure during this event. Nothing immediately dangerous, but enough to be concerning for people who fly these routes regularly. Pilots and flight attendants working polar routes accumulate radiation doses over their careers that are higher than the general population. During a severe solar radiation storm, this exposure increases further. The financial impact hit hard as well. Airlines flying longer routes, the ones that require polar navigation to be fuel efficient, were losing money on every flight that had to be rerouted. GPS-dependent industries, delivery companies, precision agriculture, surveying, and construction all experienced losses as the quality of their primary navigation system degraded. It was a pervasive economic impact, not concentrated in one sector but distributed across multiple industries. No single catastrophic failure, but many small failures adding up. The power industry was on high alert. Everyone was thinking about 1989. That was the year that a solar geomagnetic storm knocked out power to the entire province of Quebec, affecting 6 million people. The transformer that steps voltage down from high-power transmission lines to usable levels for homes and businesses are massive pieces of equipment, each one costing hundreds of thousands of dollars. During a severe geomagnetic storm, the changing magnetic field induces currents in these transformers. These currents flow through the windings, and the resistance in the windings causes heating. Multiple transformers were hit by induced currents from the magnetic disturbance. Several of them failed simultaneously. The power system couldn't handle the load redistributed away from the failed transformers. Protective systems kicked in automatically, disconnecting sections of the grid. The whole grid in Quebec collapsed. Power was out across the province. Hospitals ran on backup generators. Subways shut down. Traffic lights stopped working. Office buildings went dark. It was the middle of winter in Canada. People were worried about heating. Businesses lost enormous amounts of money. It took 9 hours to restore power, but during those 9 hours, the disruption was complete and severe. And that was just one province. The 1989 event was a wake-up call for the entire power industry. The power companies learned from that event. They've implemented monitoring systems. They watch the solar activity and the state of Earth's magnetosphere in real time. Satellites monitor the interplanetary magnetic field. Ground stations measure the Earth's magnetic field. When a solar storm is detected and heading toward Earth, the power companies receive warnings. During a severe solar storm, they can take preemptive measures. They can reduce loads on vulnerable sections of the grid. They can disconnect large equipment that might be damaged. Disconnecting a power plant that produces a gigawatt of electricity, temporarily losing that generation capacity, but saving the transformer from being destroyed. It's triage, essentially. You're making the difficult choice between a known harm, losing power generation temporarily, and a potential greater harm, destroying a critical transformer and losing power for months. It's not perfect. A truly catastrophic storm could still cause massive damage, but it's better than being caught completely unprepared. It's the difference between disaster and crisis management. During this recent radiation storm, power companies around the world were essentially in crisis management mode. Teams were standing by in control rooms, watching data streams, ready to make emergency decisions. Some power grids reduced their load. Some disconnected equipment. The situation was serious enough that it was making national news. Network broadcasts interrupted regular programming to report on the solar storm. News anchors explained to viewers that a solar event was happening and that power companies were taking measures to protect the grid. The general public, going about their daily lives, started noticing. They saw news reports. They checked social media and found discussions about the solar storm. Some people felt a sense of unease. What if the power goes out? What if we can't charge our phones? What if the internet goes down? For a brief moment, thousands of people became aware of how dependent our civilization is on reliable electrical power and how vulnerable that power system is to cosmic hazards. Yet despite all this, the lights stayed on for most people. The system held. The infrastructure that humans have built, while certainly vulnerable, proved resilient enough to weather this particular storm. But that doesn't mean we're safe. It means we were lucky. It means the storm was severe, but not quite severe enough to overwhelm the protections that were in place. It means this particular storm, while record-breaking in the modern era, still wasn't quite the absolute worst-case scenario that scientists calculate is theoretically possible. Scientists use mathematical models to estimate what a truly catastrophic event would look like. They input the maximum energy flux, the maximum magnetic field strength, and the maximum potential for transformer failure. The consensus is grim. A solar storm just a few times more powerful than this one. Not an unimaginable event, but one that's perhaps 1,000 times less likely than this one. Could cause damage to the power grid that would take months or even years to repair. Transformers that are destroyed can't simply be replaced overnight. They're massive, custom-built pieces of equipment. Lead times for replacement transformers are measured in months. If multiple transformers fail simultaneously across a large region, you don't have months of backup transformer capacity sitting around. In some regions, it could take years to fully restore service. Think about what happens when the power goes out completely. You lose lights, obviously, but you also lose refrigeration. Food spoilage accelerates. Meat, dairy products, frozen foods, all of it spoils within days. Grocery stores can't keep their doors open. Within days, food becomes scarce. You lose water treatment. Modern water systems pump water through distribution networks. Without power, water stops flowing. Within hours, water becomes unsafe. You lose sewage treatment. Waste backs up. Sanitation becomes a critical problem. You lose medical facilities. Hospitals have backup generators, and most large hospitals maintain several days to a week of fuel supply for those generators. But if the grid is down for weeks or months, the fuel supplies for those generators run out. The generators stop running. Operating rooms go dark. Life support systems shut down. You lose transportation systems. Modern vehicles depend on electronic systems for everything: fuel injection, ignition timing, transmission control. Electric vehicles obviously can't charge. Even gasoline vehicles that still use internal combustion engines depend on computers to run. Older vehicles without computers would still work, but they're increasingly rare. Without transportation, supply chains collapse. Goods can't be moved from where they're produced to where they're needed. You lose communications. Cell towers are powered by the grid. The internet depends on powered data centers. Without power, you can't call for help. You can't get information. You can't conduct business. The chaos would be immense. In the pre-industrial era, loss of power might have been merely inconvenient. In the modern era, it would be catastrophic. In a modern city, a power outage lasting more than a week is considered an emergency. An outage lasting months would be a disaster that would dwarf natural disasters like hurricanes or earthquakes in terms of economic cost. And here's the sobering part. We could have avoided many of these vulnerabilities. Technology exists to harden power systems against geomagnetic storms. Transformers can be protected by adding surge protective devices that detect and block induced currents. Backup systems can be installed. If the main grid fails, distributed generation, solar panels, wind turbines, natural gas generators can keep critical systems running. Communication networks can be made redundant. Multiple independent networks so that if one fails, others continue. Hospitals can maintain longer fuel supplies and have better generator systems. But hardening the grid costs money. A comprehensive national program to harden the electrical grid against solar storms would cost tens of billions of dollars. Upgrading transformers, installing protective equipment, building redundancy, it all costs money. And the benefit is speculative. The benefit is protection against events that might happen once every 100 years. Maybe once every 1,000 years. It's a tragedy of commons, in a way. Everyone would benefit from a hardened grid, but the cost is borne by the power companies and their customers, and the benefit is speculative. It's like insurance. You pay for insurance against disaster. Most of the time, you don't need it. Most years, you pay your insurance premium and nothing happens. But when the disaster comes, and statistically, eventually it will, you're glad you paid for the insurance. The challenge with solar storms is that the disaster only comes occasionally, on long timescales measured in decades or longer. Politicians and business leaders are focused on immediate concerns, not hazards that are statistically unlikely to occur during their tenure. That's changing, though slowly. After this radiation storm, conversations are happening again. Engineers are dusting off reports about grid vulnerability that were written decades ago. Policymakers are asking harder questions about readiness. Congressional hearings are being held. Scientists are testifying about the risks. It's the kind of event that doesn't cause immediate disaster but serves as a warning sign. It says, look, this is a real risk. We should take it seriously. And next time, we might not be so lucky. The radiation storm itself provides crucial scientific data. Before this event, we had direct measurements of solar radiation extending back about 50 years. We have satellite data from the beginning of the space age in the 1950s. We know about the severe storms of 1989, 2003, and other notable events. But predictive models are always uncertain. especially when extrapolating beyond the range of direct observations. This event, by surpassing expectations, gave scientists new information about the true limits of solar activity. It pushed the boundary of what we think is possible. The question becomes, how extreme can solar radiation storms actually get? Historically, we have evidence from other sources. Ice cores contain trapped particles called cosmogenic isotopes. When a solar radiation storm hits Earth, it creates additional ionization in the atmosphere, which leads to increased production of isotopes like carbon-14 and beryllium-10. By analyzing ice cores from thousands of years ago, scientists can identify periods when particularly intense radiation storms probably occurred. The evidence suggests that there have been events far more powerful than what we've directly observed in the modern era. The most famous historical event is the Carrington event of 1859. In early September of that year, astronomers observed an enormous solar flare. It was visible without telescopes, a remarkable rarity. The brightness was so intense that the explosion on the sun could be seen in white light against the bright background of the sun itself. The flare was followed by a global magnetic storm of extraordinary intensity. Aurora displays were visible across the entire Earth, even at the equator. Imagine being at the equator, where the aurora is never normally visible, and seeing brilliant curtains of green and red light dancing across the night sky. It would have been absolutely extraordinary. The telegraph systems, which were the high technology of the day, literally caught fire. Operators reported that their equipment sparked spontaneously. Wires became too hot to touch. In some cases, telegraph batteries were disconnected, yet current continued to flow through the wires, driven by the induced currents from the geomagnetic storm. The wires themselves became conductors of the induced currents. The systems experienced what appeared to be self-powered currents flowing through them, even when they weren't connected to their normal power sources. A system designed to operate on a few volts of direct current was suddenly subjected to hundreds or thousands of volts of induced alternating current. The insulation melted. The conductors overheated. The systems failed. If an event of Carrington magnitude happened today, the damage would be almost incomprehensible. Power grids across entire continents could fail. The failure cascade could be so severe that it would take months or even years to fully restore. The economic disruption would be immense. Estimates from researchers at the National Academy of Sciences suggest the economic damage could exceed $1 or $2 trillion. Some projections go even higher, claiming the damage could exceed $3 trillion. For context, that's a significant fraction of the total GDP of the United States. It would be economically devastating, far more damaging than any natural disaster humanity has experienced in modern times. There's a fascinating question about why we haven't experienced a Carrington-level event in the modern era. Is it just luck? Or is there something about the current solar activity that makes such extreme events less likely? Scientists don't have a definitive answer. The statistical probability of such events is low but not zero. Over a span of centuries, such events are virtually certain to occur. The fact that we've had such good luck in the modern era, with our technology dependent on electrical power, is fortunate. But it's not guaranteed to continue. Some evidence suggests that we might be entering a period of unusually high solar activity. Cycle 25, which is the current solar cycle, was initially predicted to be relatively modest. Space weather forecasters expected a cycle similar to the last one, with moderate activity. But early indicators are suggesting something different. The number of sunspots is climbing faster than expected. The strength of the solar magnetic field appears to be increasing. Activity is ramping up more aggressively than the models predicted. Active regions are appearing with increasingly complex magnetic field configurations. Some researchers have speculated that we might be entering a period called the grand solar maximum, a phenomenon where the sun remains unusually active for decades or even centuries. The last clear example was the medieval maximum, which occurred around 900 to 1100 AD. During that period, sunspot counts were extremely high. Solar activity was elevated. Before that, the Maunder minimum from 1645 to 1715 was a period of unusually low solar activity. Very few sunspots were observed. Solar flares were rare. The solar wind was weaker. Interestingly, the Maunder minimum coincided with the Little Ice Age, a time of cooler climate in Earth's history. The connection between solar activity and Earth's climate is complex and not completely understood, but the correlation is suggestive. Some climate scientists have proposed mechanisms linking solar activity to climate. When the sun is less active, there's more cosmic ray ionization in the upper atmosphere. More ionization leads to more cloud formation. More clouds lead to more reflection of sunlight, which cools the planet. When the sun is more active, more cosmic rays are deflected, fewer clouds form, and the planet warms. Other scientists are skeptical of this mechanism, pointing out that the effect size is too small to account for the observed climate changes. The debate continues, but the historical correlations are intriguing. They suggest that solar activity does influence Earth's climate, at least to some degree. If we are indeed entering a grand solar maximum, the implications are significant. We would expect more solar flares, more CMEs, more radiation storms. The statistical probability of experiencing a Carrington-class event becomes much higher. Instead of worrying about a 1 in 100 years probability, we might be looking at a 1 in 30 years or 1 in 20 years probability. Over a century, the chances of experiencing multiple extreme events become substantial. We might experience 2 or 3 Carrington-level events in a century, compared to the historical rate of perhaps 1 event per century or less. This is why the recent radiation storm is so important from a preparedness perspective. It's a data point that helps us understand what the sun is capable of doing. It helps us refine our models. It provides real-world testing of our protective systems and forces us to examine our vulnerabilities. It's a reminder that cosmic hazards are real, quantifiable, and potentially devastating. The measurement and monitoring of solar activity has come a long way since the Carrington event. In 1859, astronomers observed the flare visually with telescopes. They saw the bright outburst in white light. They noted the timing, but they had no quantitative measurements of energy, no data about particle flux, no information about magnetic field strength. Their observations were limited to what they could see and infer from the telegraph failures. Now we have satellites dedicated specifically to observing the sun. The Solar Dynamics Observatory, launched by NASA in 2010, captures high-resolution images of the solar atmosphere in multiple wavelengths. It observes the solar corona, the solar transition region, and the photosphere. It measures magnetic field strength. It watches for flares and tracks their progression. The Parker Solar Probe, launched in 2018, is actually orbiting through the solar corona, measuring conditions there directly. It comes closer to the sun than any spacecraft humanity has ever built. At its closest approaches, it's less than 4 million miles from the solar surface, incredibly close in cosmic terms. SOHO, the Solar and Heliospheric Observatory, a joint mission between NASA and the European Space Agency, has been orbiting at the L1 point between Earth and the Sun for decades. It watches the Sun and monitors CMEs continuously. The moment a CME starts to eject from the Sun, SOHO detects it. Scientists can see the structure of the ejecta, the intensity, the direction. If it's Earth-directed, warnings can be issued. GOES satellites, positioned above the equator in geostationary orbit, continuously measure the radiation environment in near-Earth space. These satellites have instruments that detect solar energetic particles, measure the magnetic field, and track the state of Earth's magnetosphere. All of these assets feed real-time data to space weather forecasting centers. The Space Weather Prediction Center, part of NOAA, operates similarly to how meteorological centers forecast weather, except they're forecasting solar weather. Meteorologists predict rain and thunderstorms using complex mathematical models that simulate the physics of the atmosphere. Space weather forecasters predict solar flares and radiation storms using complex mathematical models that simulate the physics of the sun and the solar wind. It's an imperfect science. We can't predict the precise moment when the sun will flare any more than meteorologists can predict the exact timing of rain weeks in advance. But the forecasters can identify when conditions are favorable. They recognize active regions with high-complexity magnetic fields that are more likely to produce flares. They watch how these regions evolve. When the magnetic field becomes sufficiently stressed and twisted, they issue alerts and watches. They use terminology similar to tornado watches and severe weather watches. A watch means conditions are favorable for an event. A warning means an event is happening now. The recent radiation storm was predicted, at least in its general form. When the CME was observed blasting away from the sun by SOHO, satellites detected it almost immediately. Scientists recognized that it was Earth-directed. Warnings were issued, not just to space agencies but to commercial enterprises as well. Airlines were notified. Power companies were alerted. Satellite operators were prepared. Contingency plans were activated. But the intensity of the event exceeded expectations. The particle fluxes were higher than predicted models suggested. The energies of the particles were higher. The duration of the event was extended. That's the challenge with space weather forecasting. You can predict that something is coming, but the magnitude is harder to pin down. It's like weather forecasting. You can predict that a storm system is coming, but exactly how strong it will be, exactly where it will hit, exactly how much rain it will drop, those are harder to pin down, and even small errors in the forecast can have large consequences for warning and preparation. Let's talk about the actual mechanisms that make radiation storms so dangerous to technology. Spacecraft and satellites operate in an environment where cosmic rays, high-energy particles from space, are constantly present. The magnetic field of Earth and the atmosphere of Earth provide some shielding, but in orbit, the radiation environment is more intense than on the surface. The magnetosphere shields us from the solar wind during quiet times, but during a radiation storm, the shielding becomes less effective, and we're exposed to far more particles. Spacecraft are shielded, but the shielding is never perfect. When a high-energy particle hits shielding material, aluminum, lead, or whatever material surrounds the sensitive electronics, the shielding stops the particle. But the particle's energy doesn't just disappear. It gets transferred to the material. The particle creates a cascade of secondary radiation. Electrons are knocked loose from atoms. Photons are produced. X-rays are generated. In some cases, the shielding actually makes things worse, creating secondary radiation that's more penetrating than the original particle. The internal electronics of satellites are built using transistors so small that they're vulnerable to radiation effects. Modern transistors have dimensions measured in nanometers, billionths of a meter. A human hair is about 100,000 nanometers thick. These transistors are so small that a single high-energy particle passing through one can flip a bit in memory. Modern spacecraft have error correction systems that can detect and fix some of these errors. The most advanced systems use triple redundancy, storing the same bit of information in 3 different locations. If one bit is corrupted, the other 2 can vote and correct it. But during a severe radiation storm, the error rate can exceed the correction capability. Data gets corrupted faster than the error correction can fix it. Computers malfunction. In extreme cases, components can be permanently damaged. The degradation of GPS signals during the radiation storm is a perfect example of how these effects cascade through technology and impact the real world. GPS works by satellites orbiting Earth at an altitude of about 20,000 kilometers. These satellites carry atomic clocks, the most precise timekeeping devices ever created. The clocks are so accurate that they lose or gain only 1 second in millions of years. These satellites constantly broadcast timing signals. The signal carries information about what time it is, according to the satellite's atomic clock, and what the satellite's position is. A receiver on the ground, your smartphone, your car's navigation system, a surveyor's equipment, picks up signals from multiple satellites. The receiver doesn't have an atomic clock. It has a regular quartz oscillator, much less accurate. But by receiving signals from multiple satellites, each signal carrying accurate time from different satellites at different positions, the receiver can do something remarkable. Can measure the time it takes for each signal to arrive. Because the signals travel at the speed of light, the time difference between signals arriving from different satellites tells you about your distance from each satellite. Using the distances from at least 4 satellites, the receiver can calculate its 3-dimensional position. This is called trilateration. It's the same principle used in surveying and navigation for centuries, but instead of measuring angles, GPS measures distances using time-of-arrival information. The system is staggeringly precise. Modern GPS can know your location to within a few meters, sometimes within centimeters with military-grade equipment. It's one of the most remarkable technological achievements of the modern era. But during the radiation storm, the electronics in the GPS satellites started to malfunction. The atomic clocks, so precisely engineered, so carefully calibrated, started experiencing errors. Cosmic ray hits affected the clock circuits. Tiny amounts of charge were created in sensitive regions of the clock, causing the timing to drift slightly. Just a few nanoseconds of error in a satellite's clock translate to dozens of meters of error in the calculated position on the ground. The transmitters that broadcast the timing signals became less stable. The signal strength fluctuated. The data being transmitted became corrupted. The accuracy that billions of people take for granted, that ability to know your location to within a few meters, suddenly became less reliable. In some places, GPS accuracy degraded to tens of meters. For civilians navigating with their smartphones, it wasn't a total catastrophe. The system still worked, you could still get directions, but it was noticeable. Your position on the map jumped around more than usual. Your navigation system occasionally routed you incorrectly. It was annoying, but not necessarily dangerous. But for military applications, for precision agriculture, for financial trading systems that rely on GPS timing signals to synchronize transactions across the world, for airline navigation and approach systems, the degradation was significantly more serious. Military systems that depend on centimeter-level GPS accuracy for targeting and navigation found themselves with meter-level or worse accuracy. That's not an acceptable degradation for military operations. Precision agriculture depends on GPS guidance to apply exactly the right amount of fertilizer to exactly the right locations in a field. During the radiation storm, the guidance system's accuracy degraded. Fertilizer was applied in the wrong places. Coverage was uneven. Crop yields suffered. Over the course of a growing season, this adds up to real losses, thousands of dollars per farm. Financial trading systems use GPS time signals to synchronize trades across the world. When different trading centers have slightly different times, small discrepancies can arise. Traders can exploit these discrepancies for profit. The synchronization provided by GPS timing prevents this. When GPS timing became less accurate, the synchronization suffered. Trading systems had to revert to less precise timing sources. The ability to execute certain types of trades was reduced. Communications satellites experienced similar issues. A communications satellite is essentially a giant repeater in the sky. It receives a signal from one ground station and retransmits it to another. Or it receives signals from many ground stations simultaneously and retransmits them to other ground stations. The signal passes through amplifiers and processing electronics. During the radiation storm, errors in this processing increased. Each radiation hit in a sensitive circuit could cause a bit flip, corrupting the data. The modulation of the signal, the way information is encoded onto the radio wave, became less stable. Voice signals became noisier, as if someone was listening to a radio broadcast during a thunderstorm. The quality of calls degraded. Data transmission became less reliable. Packets of digital information would arrive corrupted. Error correction codes built into the data transmission systems could fix some of the corruption, but during the peak of the storm, the error rate exceeded the correction capability. Data got corrupted faster than it could be corrected. In some cases, satellite operators proactively reduced their data rates. Instead of transmitting high-definition video, they transmitted standard definition or even lower quality video. Instead of transmitting multiple simultaneous phone calls through a single satellite transponder, they transmitted just one. They reduced the quality of service to reduce the impact of radiation-induced errors. It's not ideal, customers notice and complain, but it's better than having the system fail completely. Weather satellites, those massive instruments that observe clouds and storms and produce the data that goes into weather forecasts, started showing degradation. The instruments that measure temperature in the atmosphere use radiation sensors. During a radiation storm, the sensors themselves are hit by radiation. The detectors can misinterpret radiation hits as temperature signals. The temperature measurements become corrupted. The instruments that observe wind patterns measure atmospheric motion by tracking features in clouds. Radiation hits in the imaging electronics create artifacts that look like features, confusing the system. The data streaming from these satellites, data that meteorologists around the world depend on to make weather forecasts, became less reliable. Weather forecasters had to work with degraded data. The uncertainty in their forecasts increased. They had less confidence in their predictions. In some regions, it became noticeably harder to make accurate short-term weather predictions. The National Weather Service issued notices about reduced forecast skill due to satellite degradation. Public forecasts became less certain. The recent radiation storm actually served as a valuable test. How did our satellites perform? Which systems showed unexpected vulnerabilities? Which protective measures worked as designed and which failed? These are crucial questions, and the answers we get from analyzing this event will make us better prepared for future storms. Engineers will examine satellite telemetry. They'll identify which components failed and why. They'll design better protection for future satellites. There's also the question of satellite repair and replacement. When a satellite is damaged, it can't be easily fixed. You can't send a technician up to space to repair it. You have to wait until a replacement satellite is ready. Most satellites now have spares in orbit or in development. But if multiple satellites are damaged simultaneously by a radiation storm, the spare capacity might not be sufficient. You might have a gap in coverage while replacement satellites are launched and brought into service. Launching a satellite takes months to years. During the peak of this radiation storm, several satellites experienced anomalies serious enough that they had to be switched to safe mode. In safe mode, a satellite powers down everything non-essential and waits. It doesn't transmit. It doesn't receive. It just tries to survive. Once the radiation storm passes, engineers have to carefully work through procedures to bring the satellite back to normal operation. This takes time. For days or weeks, the satellite is offline. The cascading nature of these failures is what makes radiation storms so concerning. It's not just one system failing. It's many systems degrading simultaneously. Communications degrade. Navigation becomes less accurate. Weather forecasting becomes less reliable. Power systems have to be managed more carefully. The entire technological infrastructure becomes more fragile, more prone to failures, more stressed. And yet, despite all this, the systems held. No catastrophic failures. No cascading blackouts. No complete loss of any critical service. The infrastructure proved more resilient than the worst-case fears. But that's no guarantee for next time. That's no guarantee that the next storm won't be a bit stronger, pushing systems past their breaking point. This is why scientists take solar storms seriously. This is why space agencies invest in monitoring the sun. This is why power companies maintain watch over space weather data. The next major storm could be worse. The next major storm could be the one that causes significant damage. And there's no way to prevent solar storms. We can't go up to the sun and ask it to please stop producing flares. We can only prepare ourselves for the inevitable and hope that when the next major event occurs, we're ready. The science of understanding these events has evolved tremendously over recent decades. We've gone from visual observations by astronomers to continuous satellite monitoring, real-time particle detection, and sophisticated computer models. We understand the physics of the sun far better than we did even 50 years ago. We know how magnetic fields can store energy and release it catastrophically. We know how shock waves accelerate particles. We know how the solar wind interacts with Earth's magnetosphere. But there's still much we don't understand. We can't perfectly predict where a flare will occur. We can't perfectly predict how powerful it will be. We can't perfectly predict how a CME will interact with Earth's magnetosphere. These uncertainties are because the sun is fundamentally a chaotic system. Chaos, in the technical sense, means that tiny differences in initial conditions lead to vastly different outcomes. We can't measure the sun's state with infinite precision, so we can't predict the sun's behavior with infinite precision. This is actually comforting in a way. It means that no matter how advanced our science becomes, there will always be surprise and unpredictability in the universe. It means we can never achieve complete control over our environment. It means we have to maintain a degree of humility about our place in the cosmos. the universe will always be capable of surprising us.